Vacuum is a very good insulator. What will happen if we place two metal electrodes in high vacuum, spacing them about 1 millimeter apart, pump it down to about 10 to the -6 torr, and then apply some voltage across the electrodes? There is positive 5 kilovolts on the tip of that cable. Yes, 5 kilovolts. No kidding. What is about to happen? Exactly nothing, as expected. Now watch the magic. This is our magic slurry. All it takes is just one drop of it applied to the end of the negative electrode. Then let it air dry. Then bake it. Then perform this one magic step. And then repeat the same experiment. We start with just 2.5 kilovolts. What do you think will happen? We have current, an electric current going through that 1 millimeter gap in high vacuum between the two metal electrodes. How is this even possible? There is obviously no heated filament here, which would normally be expected as a source of free electrons. So, what exactly was in that magic black slurry we've applied to the negative electrode? Our black slurry is a simple mixture of carbon nanotubes and silver nanoparticles. Carbon nanotubes, or CNTs as we called them, provide the free electrons via field emission, while the silver nanoparticles are used to bond the CNTs to the surface of the metal electrode. This is how the surface of the metal electrode typically looks like after applying the mixture of CNTs and nanoparticles. Note the individual CNT fibers visible under the scanning electron microscope. They are the source of the free electrons. The current density of CNT emitters is described by the well-known Fowler-Nordheim equation from the field emission theory. One could take the current readings versus the applied voltage for a CNT emitter and calculate all the parameters of the equation. This is a purely academic exercise, though. The most important practical value is the ultimate achievable current density. My humble DIY CNT emitters, which are 1.6 millimeter in diameter, produce between 200 to 500 microamps, resulting in the current density of between 10 to 25 milliamps per square centimeter. According to many research papers, this is a rather average performance, which I guess is not that bad for such a crude DIY electron emitter. Carbon nanotubes are surprisingly easy to obtain. These multi-walled CNTs were available at Amazon. They worked fine. These no-name CNTs can be found on AliExpress. Unfortunately, these CNTs are rather dirty. They first need to be calcined in air to get rid of all the amorphous carbon, and then they need to be washed in hydrochloric acid to get rid of the iron catalyst. However, after the cleaning steps, these CNTs then work even better than the previous ones. They are also about 1/3 of the price. The second component of our slurry is silver nanoparticles. This glass vial is not empty. It contains about 100 milligrams of 30 nanometer silver nanoparticles. And this is the same 100 milligrams of nanoparticles when dispersed in isopropyl alcohol. There are a few companies which offer silver nanoparticles for sale. However, these are often rather expensive, but even worse, I could never figure out if the nanoparticles produced by a particular method would be suitable for this particular purpose. For example, whether they could be easily dispersed in IPA into a nanoscale slurry as opposite to a macroscale slurry. Therefore, I ventured to produce my own silver nanoparticles. Looking back, I most certainly do not recommend this route, but still this can be done if no other options are available. There are a great many research papers about producing a tiny amount of silver nanoparticles. There are a lot less papers about producing silver nanoparticles in bulk quantities. And then among those papers, there are quite a few which are simply not reproducible. Yes, I found this the hard way. Finally, there was one which has worked. It used common chemicals, and it produced nanoparticles of a size just large enough to be separated by a budget-friendly centrifuge. Still, it is a 4-hour cooking step, followed by multiple 2-hour-long centrifuging steps, all to obtain this almost empty vial with just a 100 milligrams of the final product. And to add insult to injury, the final yield was just 8%, meaning that 92% of silver went down the drain. Finally, with both the CNTs and silver nanoparticles obtained, it is a simple mixture of about 1% of each of them in IPA, sonicated for about 15 minutes to produce the magic black slurry. The slurry is then applied with a pipette to the tip of the negative electrode and let dry. One can then repeat with another drop of the slurry if needed. Finally, the metal electrodes are baked at around 300 degrees Celsius to sinter the nanoparticles. For silver electrodes, this baking step can be done in air, while for copper electrodes, it has to be done in argon. Here's the poor man's argon flow system for my furnace. I also tried tungsten electrodes, yet those showed very poor adhesion with silver nanoparticles. I have since just used pure silver for the electrodes. This last weird step is actually necessary to condition the CNT surface, to remove loosely held CNTs, and, most importantly, to help align the individual CNT fibers vertically. This step significantly increases the final achievable current density of the emitter. Here's the surface of the silver electrode with the CNT slurry applied and baked in. One can see that it is obviously not perfect, but again, this is still good enough for many uses. Not to mention that the proper techniques of attaching the CNTs to the metal substrate are still an active area of research. There is one more test we can do with our CNT emitter. We can look at the emission density distribution over the surface area of the electrode. Let's replace the second metal electrode with a small piece of FTO glass. The glass conductive surface is facing the emitter. It has to be the FTO glass and not the ITO glass, as the former is mildly fluorescent under the electron bombardment, which is the property we need here. This is a slightly magnified image of the emission surface. My humble understanding is that, in the ideal case, this image should be a uniformly bright disk. Well, this is obviously very far from the ideal case, showing a few very bright spots, with the rest of the emitter being mostly dead. Our crude technique of coating the electrode surface with the CNTs is not very good at creating uniform emitting areas. On the other hand, this particular emitter wasn't freshly made. It's been sitting idle for about a month, exposed to air. This could contribute to its emission uniformity being this bad. It is amazing that the emitter still works. These CNT emitters are actually quite robust. Still, assuming that all the emitted electrons are eventually to be focused into a much smaller spot, the intensity distribution inside of that focused spot is not critical or even important for many applications. Like, for example, in this modified Steigerwald-style electron gun, which I am planning to make as the next step of this project. The electron beam is to be focused into a 0.5 millimeter spot. It works great in simulation, but will it work in practice? We will soon find out. Thanks for watching.